Okay, so systems of linear equations. This is from the Edexcel further maps. It's part of chapter 6 in Core Pure 1 to do with matrices. So yeah, let's talk about what's going on. Hopefully you've seen at this point, when you have a system of three simultaneous equations in three variables each, you can represent the system of equations as a single matrix equation. So we take a matrix here with all the coefficients of the equations, and we multiply by sort of an unknown vector x, y, z, and that's going to equal to our constant vector on the right hand side. If you multiply out this matrix equation, you get exactly the three equations on the left. And just for sort of notation and abbreviation, let's just call this big matrix A, let's call the unknown matrix X, and the known matrix B. So three simultaneous equations turns into one matrix equation, AX equals B, where X and B are vectors. And this whole topic is about classifying what can go on, what can happen with these solutions, and you can tell a lot just from the matrix A. So what you can tell is, and this is kind of like the boring case. The boring case is if the determinant of matrix A is not 0. So the first thing you do in these questions, you check the determinant. Because if the determinant is not 0, that means that the matrix A is invertible. Okay. Now, hopefully you've done a little bit of algebra with matrices, and what you've learned is if a matrix is invertible, what that means essentially is you can divide by the matrix. You can move a matrix onto the other side of the equation by multiplying by its inverse. So, for example, here, I've got a different colour pen. Okay, instead of AX equals B, that is the exact same thing if A is invertible as saying that X is A inverse B. And it's actually just our solution for X, right? It's X equals. And what it is really important here is a unique solution. Okay, so if A is an invertible matrix, there is exactly one vector, x, y, z, which solves the system of equations. So it's exactly one solution. So a unique solution. In this case, I'm not going to go through all the algebra, but if you take this matrix A, you find the inverse, and if you multiply by 336, you'd actually find out that X is 112 in this case. So you can go try that if you want, like an exercise. But yeah, one single unique solution is a matrix is invertible because that just means you can just divide by A essentially. Only one possible solution. This topic gets interesting when we talk about the other cases. So what else can happen? We're going to break the two cases down into when our system of equations is consistent versus when it is inconsistent. So a system of equations is consistent if there is at least one solution. So a solution or multiple solutions. As it turns out, and this is actually not obvious, but as it turns out, the number of solutions is either 1 or infinity. Okay, you could never have like just 2 or just 3 solutions. If there's multiple solutions, there will be infinitely many. That's the only possibility. So, and I mean, the case when there's only exactly one solution we've kind of already dealt with. This is when the matrix was invertible, which means the case of infinite solutions must be when the determinant was 0, the matrix is not invertible. Okay, and likewise, we will say our system of equations is inconsistent if there is no solution, right? The equations are inconsistent if there's no values of x that makes the three equations work. So again, if you think about it, this cannot be the case where the matrix is invertible, because invertible means there's one solution. This must also fall under the case that A equals 0. So these questions, we take the determinant. If it's not 0, easy, done. One solution, unique solution. If it is 0, we have to decide, okay, is it consistent with infinite solutions, or maybe is it inconsistent with no solutions? So, like, how do we check? This is how we classify, how to check. And we'll do this one as an example. And then we'll talk about geometric interpretation in a bit later. So how to check? Well, you're going to take your equation. This is, once you've checked the determinant and determinant is 0, you now want to sort of work back from the original equations rather than with the matrix form. Okay, so I'm going to go back to my original equations. think what I can do actually is just copy these down. And what you want to do with the equations is solve them like, if any of you did GCSE Further Maths, the way you solve systems of three equations there. Brilliant, copy. And then paste. Yeah. So how would you solve these system equations back in GCSE Further Maths? Well, what you do, you pick two of the equations, let's say equations 1 and 2, and you choose any variable to eliminate. I'll choose z, purely because it's easiest. I can just add the two equations and eliminate z. So adding will give me 5x plus y equals 6. Eliminate z. And same exact thing, choose two different equations, so 1 and 3 or 2 and 3, eliminate the same variable. Okay, this was the method. Let's eliminate z again. This time I'm going to have to, actually that's also quite easy, isn't it? I can just, again, add the two equations. I did wrong. This I've gone wrong. This matrix, if you check its determinant, was not 0. The matrix was invertible. What I meant to add in, if I changed this number here to a -2, now actually the matrix is not invertible, the determinant is 0. So if I change the equation to take away 2z, okay, so this is my equation. I did the determinant was 0. Oh, I have to go back in. I have to, eliminate. So let me just fix this here. Add a -2. Okay. Right. Sorry about that. So yeah, now I eliminate z. I'm gonna have to double the second equation and then add on the bottom equation. Okay, so that'll give me 5x. What will give it plus y equals 12. And you might notice, get a bit of a pattern on the right. Okay, both equations tell me the value of 5x plus y. Now this will always happen. If you're in a situation where the matrix is not invertible, this will happen, right? Okay. If the matrix was invertible, like before I fixed it to a -2, what you get is easily solvable. You just eliminate a further variable, get x or y, and then sub back in. You can see here the issue is I can't eliminate just x or just y. I eliminate both of them at the same time. So this system of equations would either have infinite solutions or no solutions. And, well, can 5x plus y be both 6 and 12 at the same time? No, it can't. So this would be an inconsistent system of equations with no solutions. Sometimes what you get, it might not be 5x plus y on both, but the second one might read 10x plus 2y equals 24, right? And then you would still be able to determine whether they're consistent or inconsistent because that bottom equation is a multiple of the top equation on the left, but the right sides are not consistent with each other. Okay, so if you do this whole process, let's go back a little bit more. If you do this whole process, but in the end, let's say I had a 6 here and a 6 here, then that would now be consistent and there would be infinite many solutions. Okay, so checking it is not too bad. We get the equations, we eliminate a variable from both, and we see if the equations we get agree with each other or don't agree with each other. Okay. So next up to talk about was just the geometric interpretation, and then we'll kind of do like a flow chart, overload, recap the whole thing. Geometrically, you should know from chapter 9, an equation like 3x plus 2y minus z equals 3 is actually a plane. Okay, in three-dimensional space, it describes all points lying in a two-dimensional flat plane. So we have 3 planes. And the solution to simultaneous equations will be what point satisfies all 3 equations. So which point is on all 3 planes. And yeah, if the matrix was invertible, so let's go through all the cases again. I'll just draw a picture. If it's invertible, we know the unique solution, which means there is exactly one point which lies on all the planes. So we will say the planes is a unique solution. The planes intersect at a single point. So I'm going to do my absolute best to try and draw this here. There's much better pictures available, say in the textbook or elsewhere online, but let's give it a go. Here's one plane. Here's another plane. And they kind of intersect on this line. So two planes in general, as long as they're not parallel, they'll meet along a line. And let's say the third plane just comes in, I don't know, like here. And yeah, I think these three planes are kind of intersecting right here, let's say. So there's, and what you would say to describe it is you say the planes meet at a single point. Make sure in the exam you're using the word plane in there to get that geometrical interpretation. Okay, so the two more interesting cases where was when det A was 0, and you go and check is it consistent or inconsistent. I'll need more room here, won't I? So if it was consistent, meaning infinitely many solutions, that means there are infinitely many points that are on all three planes. So in general, again, I'm kind of ignoring the possibility of parallel planes. I'll maybe just add that on quickly at the end. In general, that's going to mean is your three planes, when two of them kind of intersect in a single line, the third plane also intersects on that same line. So what happens is there is a line which is common to all three planes. And the geometric interpretation or the description is that the planes form a sheaf. Okay, so you've got three pieces of paper, but they all share one line, which means any point on this line is a solution to the simultaneous equations, which is why there's infinitely many. Okay, it's also why you can't have just two solutions, right? There's either a point, one solution, or a line, so that's infinite solutions. The second interesting case was when the determinant was 0, but it was inconsistent with no solutions. Again, ignoring any possibilities of parallel planes, the only way you can have three planes, non-parallel, non-equal, where there's no common points of intersection, is if they form a triangular prism. Okay, so the planes form a prism. You can see there's no point common to all three. They form a triangle, essentially. It's prism because it's 3D, but it's essentially a triangle. So, if I was to sort of recap it all in a flowchart, I would say step number 1 would be to check determinant. What is the determinant of that matrix? If the determinant is 0, sorry, let's do not equal to 0 first. Then we know we have a unique solution. So it is consistent because there is a solution. And we know the planes meet at a single point. And to find that single point, you could just say that x is A inverse B. Just calculate it by inverting the matrix. And the second possibility of determinant is if it is not 0. So if it is 0, in which case you do the algebra. Okay. And if your algebra spits out, let's say it spits out something like x plus 2y equals 5 and 2x plus 4y equals 9, we can see these two equations are not the same. They're sort of two parallel lines that don't meet. So this is going to be, I guess I'll do it in a box to match it. It's going to be inconsistent, no solution, and I will say that the planes form a prism. Okay. No values of x and y make both of these true. It's impossible, right? Because if x plus 2y is 5, then 2x plus 4y would have to be 10. If when you do the algebra, you get something like, and it might not look exactly like this, but x plus 2y equals 5 and 2x plus 4y equals 10, so they're agreeing with each other, yeah? This is how you know it's a consistent system of equations with infinite solutions, which lie along a line. So I say the planes form a sheaf. And that's kind of like your flowchart. This is all you really need. Determinant, and then if determinant is not there, if determinant is 0, you do some algebra. And it's easy to remember if you know the theory, if you know that, well, when the determinant is not 0, I can just invert the matrix and divide. So it's just nice and boring. And then when I can't do that, it's more interesting. Yeah. The thing to mention as well, I'll mention about parallel planes. It's not too bad, but the geometric interpretation might change if, for example, you have some of your planes are parallel. So let's say I have two parallel planes that are non-equal, and then a third plane cutting through. Just geometrically, I can say it's inconsistent, right? Let alone let the third plane come into it. There's not even a common point on the first two planes, the parallel ones. So I know immediately my A here would have to have determinant 0, because if the determinant was not 0, there would be a solution. And you could say two of the planes are parallel. You could have like 3 parallel planes. You could have 2 planes that are like where 2 are on top of each other that are exactly equal. And then the third one is kind of just sticking out randomly. And here it's actually a special kind of sheaf. There is a line of solutions, yeah? So this would be actually consistent with infinite solutions. This is the same here. Actually, if any of your planes are parallel at all, you will have det A equals 0. And how do you tell if your planes are parallel, right? It's easy to tell. Planes are parallel if the rows of the matrix are multiples of each other. So, for example, if I had 2, 3, 7, and 4, 6, 14, and then the last one could be anything, okay, pi 1 and pi 2 would be parallel planes. And they would be equal planes, the same plane, if the right-hand side kind of matched up, like 2 and 4, because then they both describe 2x plus 3y plus 7z equals 2. And the two planes would be parallel but sort of non-equal if maybe they disagreed, right? So they're not consistent with each other. So that's to do with the right-hand side, whether they are equal or non-equal, but just the actual row of the matrix, that's what determines whether they are parallel in the first place. In exam questions, this has not come up yet. I'm not saying it could never come up, so it's good to be aware. So do also check that none of your rows of your matrix are sort of multiples of each other, but if that's not the case, you can just follow your simple flow diagram. And yes, this diagram here. And just to sort of like illustrate what you can kind of get asked, like sometimes, for example, they might tell you that it's consistent or inconsistent and have you find an unknown value. So, e.g., let's say if I just alter the question ever so slightly, so e.g., let's say the matrix was practically the same, but it was 1, 3, and p, unknown p, and x, y, z equals 3. Actually, let's make it this -2. Right. But what we're going to do, we're going to make this one p here. And they say this is consistent, and it says find p. Okay, what would you do? Well, you can kind of tell from the word in the question that it's not going to be a unique solution because that would be nothing to do with p, right? If the matrix was invertible, it would be consistent already. You can check the determinant to solve it. You can check the determinant. It does give you 0, so you have to go and do the algebra. And we know the algebra will be consistent in the end. There will be a solution. So 3x plus 2y minus z equals 3. 2x minus y plus z equals 3. And this is x plus 3y minus 2z. So similar to what we had before. Now I know it's going to be consistent, so maybe let's just, for the fun of it, let's just eliminate a different variable. Probably would still choose z here just to be straightforward, but just to give you another example, let's eliminate y. So top equation plus twice the middle equation will give me 7x plus z equals 9. And 3 times the middle equation plus the bottom equation will give me 7x plus z equals, what's that? 3 times this one plus that one, 9 plus p. And because I know it's consistent, I know the equations have to say the exact same thing, and these equations say the same thing, because the left sides are equal, it means the right sides are equal, which means 9 has to be equal to 9 plus p, which means p would have to be 0. That would be my answer. P equals 0. That means it's consistent, there's infinitely many solutions. Any value of x and z that makes this true, and then a corresponding value of y that sort of fits in with the other equations. Okay, so I hope that kind of summarizes this topic and the fact that it's really all to do with the determinant, and just you only have to go in and analyze the algebra, right, if your determinant was 0, and then it's just a case of whether the equations you get when you eliminate one of the variables are harmonious and agree with each other, or whether those equations disagree. And just learn these geometric interpretations and things to say as well. And that should be good for the topic. So good luck with the revision.